Hello and welcome to maybe the second class on phenols, and possibly we shall be finishing phenols and going to ethers. Ethers is common to both aromatic and aliphatic. It may contain both aromatic parts like diphenyl ether, or it may be having methoxy, benzene, or anisole having both aliphatic and aromatic. So ethers is common to both. So to continue, before we continue, I would like to give you a roadmap problem quickly. You have to uh, course you might be just I give you a, here in a wild guess to predict B, because we have not studied that so far. MA, what is MA? Mixed acid, which is conc nitric acid, conc sulfuric acid. And you can make a wild guess what happens when A is treated with reducing agent like teen conc HCl. And rest part you know. What is A?
Nitrobenzene.
Precisely. This is nitration. We had studied in our arenes, chemistry of arenes. Then this we have not. But you can make a wild guess. What would be B? B, Samida? Rudra?
Chlorobenzene.
Teen HCl is a specific reducing agent to convert NO2 to NH2. So it will be aniline. That's why I told we have not studied that. That will be coming in the aniline chapter. Preparation of aniline, we have not, amines. So we have not done that, but I wanted to make a wild guess. Nitro is converted to NH2 by teen HCl. There are many. Zinc HCl also is possible. But the best one is teen HCl. And then, do you know how to convert?
Yes,
What is C?
diazonium salt.
This is BDC, N2 plus, Cl minus. There's an N triple bond. So we usually write N2 plus, Cl minus. BDC, benzene diazonium chloride. And last time we learned that when that happens, there is a SN1 mechanism, phenyl carbocation, which is though unstable, it happens. And then second step. So what is D?
Sir, phenol.
Phenol, yes. Once you get phenol, since this is acidic and both Na and NaOH can repeat out, so we get this one sodium phenoxide, the salt. And then this is a Williamson synthesis. We shall be doing that in our ethers program. And because we can't take chlorobenzene for getting ethoxybenzene. There will be no substitution SN2 at an sp2 hybrid carbon in chlorobenzene. So if you want ethoxybenzene, then you have to take sodium phenoxide, make phenol, make sodium salt, and then have SN2 with ethyl bromide or ethyl chloride. So this will be SN2. So you will get F is ethoxybenzene. That is an ether about which we shall be discussing. So this is ethoxybenzene. Got it? Understood, Mr. Tripathi?
Yes, sir.
Okay. I think we will not delay. We'll be doing a lot of such roadmap problems later when we finish. But still, I am inclined to go for the second one. Uh, mm, yes. Done. Welcome, Shruti and Shreya.
Good
Uh,
evening, sir.
we are doing some roadmap problems. This is the second one that we are doing now. Isopropyl alcohol treated with chromium 6 oxide in presence of sulfuric acid and dissolved in acetone medium, and we know that is called the Jones reagent. To give A is treated with a Grignard reagent ethyl magnesium bromide followed by hydrolysis to give B, and B is subjected to treatment with red hot copper to give two compounds C and D. Maybe one of them is major, the other one is minor. Over?
सर बी जाए
Are you kidding me? You have gone up to B and you cannot move ahead. This is something like kidding me. What happens when 3-degree alcohol is subjected to red hot copper treatment? We are studied in the chapter alcohols, and you have completely lost it. What will be A? What will be A?
सर एसीटोन
Definitely, 1-degree alcohol gives in this Jones reagent gives carboxylic acid via aldehyde. It's difficult to control the oxidation process unless you take PCC or DMP. some specific or MnO2, some specific mild oxidizing agent which has not the capacity to drag the oxidation towards the end, that is carboxylic acid. So but in secondary alcohol, you get this will be going with the oxygen, for example, by this. So give acetone. So A is acetone, and then any ketone with a Grignard reagent in the preparation of alcohols, we know that this is nucleophilic addition. So the ethyl group joins here, and when it is hydrolyzed, you get a tertiary alcohol. Ketone gives a tertiary alcohol after hydrolysis. So ethyl joins here. So you get this compound. This is, we can call it third pentyl alcohol or 2-methyl butan 2-ol. And we know, although 3-degree alcohols are resistant to normal oxidizing agents, no reaction unless you go for a a drastic conditions. Otherwise, it will not react. But copper and heat will react in a different way. What will be the products? C and D. Anyone? Miss Misra and Miss Misra? Miss Tripathi? Mr. Rudra?
No, sir.
Are you kidding me? You see your copy in the chapter alcohols, in the point catalytic dehydrogenation. After oxidation, you have a point catalytic dehydrogenation. See to that point and tell me. 1 degree alcohol gives aldehyde. No room for any further oxidation. 2-degree alcohol gives ketone, but 3-degree alcohol undergoes something different in the name of catalytic dehydrogenation. It undergoes what? Anyone? Just refer to your copy, Rudra.
Sir,
That,
aldehyde one.
huh?
Aldehyde one. Aldehyde one.
Are you kidding me? I am now suspecting.
वाटर डबल वन मैंने वाटर रिमूव की डबल वन CC.
Yeah. There will be a dehydration process to form an alkene containing same number of carbon atoms. Whenever an alkene is formed, there will be regio selectivity. The more branched alkene is the major, the less branched alkene is the minor product. So here there will be beta elimination CH. Only on heating, in presence of copper. So that gives the major product. Let me make a little bit twist in the structure so that we bring double bond in the straight direction. So this is one compound, double bond CH3. The other one will be going to either this or this, so that you get, this is supposing C major and this is minor. So you can have it here. This is minor. So have we not studied Samhita?
Yes, sir.
So you guys are not revising. I'm thinking that you are revising it and capturing them, but you are not. That is not giving me a good, impression. I'm sorry to say that this is a very small little thing that you are supposed to do. Okay. Another one. So while I was teaching to regular students the heterogeneous composition, I was spending a lot of time in revising things through roadmap problem with all the topics still taught, which I am avoiding here because I am thinking that you are doing the required homework to capture these topics. Done?
sir ଟିକେ
This is butane, but-1-wine, not only butane, because butane has two isomers, but-1-wine and but-2-wine. So but-1-wine is subjected to mercuric salt treatment in an acidic medium with a mild warming to give A, and then LH is lithium aluminum hydride, followed by hydrolysis to give B, and then PCl5C, then you are treating with sodium ethoxide.
yes sir
So what is A?
স্যার এ হচ্ছে বিউট টু অন বিউটান
Butan,
টু অন বিউটান
butan
টু
2-on, because this is hydration process. OH will be joining here, H will be joining here. So it is enol, this will be enol, and then ketoenol. This enol is unstable, so there will be hydrogen coming here, double bond going there, and so that you ultimately get a ketone. I remind you that acetylene is the only alkyne which gives acetaldehyde. Other alkynes gives ketones. If you are having an internal alkyne, for example, but-2-wine, say but-2-wine has no other option. But-1-wine and but-2-wine will give the same product, butan 2-on. But if it is pent-2-wine, then you get a mixture of pentan 2-on and pentan 3-on. That is why we uh, have this is good for terminal alkynes to give mm, a unique product. Is a 2-on. Always a terminal alkyne gives 2-on. But I remind you, I don't know how we have done or not. Maybe we shall be doing in aldehydes and ketones chapter. Let me tell you, you tell me whether I have told this before. That is, if you take a bulky hydride like Cr2BH, dicyaamyl boron hydride, and do the hydroboration oxidation process in a terminal alkyne, instead of getting ketone, you get an aldehyde because the steric hindrance will not allow 3-borane to BH3, BH3, BH3. This will not be BH3. It will be only BH with a huge, dicyaamyl group. It will be two CML. CML is both sec and isoamyl. From the beginning, there will be iso structure, and at the end, there will be sec structure. So ultimately, you have a carbon having one hydrogen left that being the ultimate alkyl group, which will be connected to connected to aluminium. So there are two such groups. Sorry, connected to boron. I'm so sorry. Connected to boron. It's not BH3. It is Cmil whole 2 BH. Once one hydrogen is added, another one will not go for a second. So it will remain in the double bond stage. Since it is Markovnikov addition, hydrogen will be joining because hydride is more negative. It is going to the inner carbon, the second carbon, and the use B with Cml2, 2 Cml will be joining in the terminal one. So you can't make a double bond into a single bond. It will remain as such. And then on oxidation with hydrogen peroxide, you will get terminal enol. The terminal enol will convert to aldehyde. So that is a very interesting way to get aldehyde from terminal. But if you take mercuric salt, you get a ketone. And some people ask, why do we use dicyanamyl borane? Why not for internal alkynes? It's not recommended because an internal alkyne will give ketones. So why there will be a steric crowding and the reaction will be slowed down instead of taking mercuric salt, what we learned now. Instead of taking mercuric salt, if it is but2-wine, it is symmetrical compound, you get only butan-2-on. If it is pent-2-wine, you are definitely getting two ketones, pentan-2-on and pentan-3-on. That is a better method. Then you can separate by many methods, many other methods that are there to separate. Of course, they are positional isomers. They are positional isomers. They have different properties. So you can take the best property which can be harnessed. The method like fractional crystallization, fractional distillation, any method you can use because they are functional isomers. Their physical properties are not same. They are different. So that dicyanamyl method is applicable or mostly applied for terminal alkynes. Have we discussed that, Master Rudra? No.
No, sir.
No. We'll be doing that in aldehydes and ketones. Okay. Then you have this is butan-2-on A. Then what is B?
Sir, alcohol. Alcohol.
This is a secondary alcohol because ketone with reduction will give you H here, one H here, one H here. So it will be CHOH. This is a 2-degree alcohol. And 2-degree alcohol, whatever may be the alcohol, PCl5 will make it chloro. This will be a 2-degree halide. Now your knowledge about haloalkanes can be used. What are the two ultimate products that I have asked for?
Sir, ମାନେ ପ୍ରାଇମେରୀ ଆଲକିନ୍ ବନିବ ଆଉ ମାନେ ETOH alcohol ବନିବ।
Are you kidding me? Alcohol na ether. There is sodium ethoxide. I have given sodium ethoxide. Alcohol kono? এটা কোন হাইড্রোলিসিস ହେଇଛି কোন সলভোলিসিস ওয়াটার অ্যাড করছে না we are adding aqueous KOH. We are doing sodium ethoxide, which is a strong ethoxide ion is a strong base. Of course, we are using alcoholic medium. Of course, in alcoholic medium there is a problem because there will be some alcoholysis, but the product will be same. Doesn't matter. So alcohol ethanol is good. Now since OET minus is a strong base and is a 2-degree alcohol, the major product will be elimination. And elimination, of course, I could have given E plus D plus D plus F. So when you take the elimination product, there will be always, since it is internal haloalkane, so you get a mixture of, and in fact, if you take the diastereomers, there will be cis and trans. I can make it D, E, F, G. So supposing this is Z and E plus E. So this is D plus E. And of course, there will be some amount of but 1 in. So elimination is over. C, D. I'm sorry, C, D. Huh? D, E, sorry, D, E. D plus E. This is F. And then coming to the SN2 substitution, that is Williamson synthesis, because this is sodium salt and this is a 2-degree alcohol. This will be minor product. This together, cis and trans, and out of cis and trans will be major. But butene is the major product. It is more substituted alkene. This is the minor product. Among the elimination, among butene, trans will be major, cis will be minor, and the real minor product will be not very minor, but maybe 40% will be substitution, maybe 30% will be substitution SN2, and that will be giving you this CH. This is OET. OET will substitute the Cl, giving you the Williamson synthesis of ether. This is what we can call it 2-ethoxybutane or sec-butyl ethyl sec-butyl ether. Got it?
Yes, sir.
Uh, so I think I would like to spend time in solving this problem. Acha, well, let me go to another one. Let me see how far you can analyze. So how you can convert, supposing I give you methanol and I want this one, ethanol, so that you have the entire laboratory with you. You have to use only inorganic reagents and organic conversions. These are called conversions. So for conversions in the examination, for aliphatic compounds, particularly aliphatic compounds, not aromatic, you need to only take inorganic reagents. You cannot take an organic reagent like Grignard reagent, whatever you choose. Accordingly, Grignard reagents are so very helpful in synthesizing many types of compounds, starting from alcohols to next time you see aldehydes and ketones, carboxylic acids, esters, derivatives. But you can't take organic reagent. Grignard reagents are organometallic compounds, organic as well as inorganic combined. There is a carbon metal bond in all organometallic compounds like alkyl lithium, phenyl lithium, or Grignard reagent, or dialkyl zinc, dialkyl zinc. These are dialkyl magnesium. These are all organometallic compounds. You can't use that also. So, anybody who can give a plan how to step up? I have given you one carbon. You have to yes.
तो अगर मैंने हेलोजिनेशन कर दो
Huh?
हेलोजिनेशन
Yeah, you have to bring it to the haloalkanes because haloalkanes are substrates for carrying out both substitution and elimination. So, in every conversion, usually we have to bring it to haloalkane. So, tell me, you use PCl5 or SOCl2 or PCl3 to make it CS3Cl. Next.
फिर कार्बन ऐड करे को कैसियन ऐड करे
Yeah, Cassian is very good to increase the number of carbon atom by 1. Cassian, one of the best methods. And I have told you last time that cyanides on hydrolysis, although we have not officially studied that, cyanides on hydrolysis gives carboxylic acid hydrolysis. Then we have not yet studied carboxylic acid chapter, but in the preparation of alcohols, we have used them, how La can be used both for aldehydes, ketones, carboxylic acids, and esters to bring alcohols. So, see, he is saying, let us use KCN alcoholic KCN, so that you can get cyanide will be substituting chloride. So you get CH3CN. By that, one carbon is already enhanced. Then, another step is H3O plus. H3O plus, any cyanide, alkyl cyanide or alkane nitrile on acidic hydrolysis will give you the corresponding carboxylic acid and ammonium ion. Ammonia cannot escape. It will be trapped by H plus to produce NH4 plus, but we don't write. We only write the organic mm, product. Now we have to go for La. Lithium aluminum hydride followed by hydrolysis will make it, because I told you aldehyde and carboxylic acid, they behave similarly to produce 1 degree alcohol with La. The only difference is that aldehyde ketone can be also reduced by the younger brother of La, the sodium borohydride, which cannot be used to reduce carboxylic acid and esters to produce alcohols. In case of esters, you get two alcohols. One is primary, the carboxy part, and the alkoxy part will give you alcohol depending on the nature of R. That we know, we are not starting revising them. Got it?
Yes, sir.
But Samita and Miss Mishra and Miss Mishra, we have another method, particularly to make the carbon atoms doubled. एक के दो, दो के चार, तीन के छह, ये तो आराम से हो जाएगा भाई ऊर्ज कपलिंग, ऊर्ज रिएक्शन. So here we could have chosen sodium ether to get ethane. And then bromine, don't take chlorine. Chlorine is, the selectivity is very low. You get a mixture of even monochloro, dichloro. Here you will get only one monochloro. Ethyl chloride is the only monochloro. There is no isomeric monochloro alkanes from ethane. But if it is propane, you get both one chloropropane, two chloropropane. Maybe successive chlorination can happen. But if you take bromine, though slow, it is highly selective. One substitution will be taking place, not multiple substitution. So bromine, HNu, heat, so that you get CS3CS2Br. Then you can directly go for aqueous KOH. Aqueous is a very funny concept for me. KOH, you can write according to your NCERT book. For getting alcohols, you take aqueous KOH, and for getting alkene, you take alcoholic KOH. This is silly. Anyway, since it is 1 degree halide, the only product will be, the predominant product will be the alkane, CS2 double bond CS2. Will be the substitution product. That is what we wanted, ethyl alcohol. The substitution product will be the SN2 substitution will be happening here. So how many steps you got in this route? One, number of arrow marks, 1, 2, 3. In this step which Mr. Rudra proposed in cyanide 1, 2, 3, same. It's not economical. So more economical the conversion is, you will catch more attention from the examiner or anybody will look at it. That means you have got a thorough knowledge of everything. Therefore, you devise a route which is the most economical. Now, supposing I ask you to do the reverse, how to convert? I have a lot of ethanol. I want to make it ethanol. In the laboratory, I can perform multiple sequential processes, reactions, so that ultimately all alcohol I have, I make it methanol. So here, to reduce the number of carbon atoms by 1, I have not told you any method. We will be doing that in our carboxylic acid chapter. Huffman bromamide reaction. I'm not going to, but here this is simple.
सर कोलबेस इलेक्ट्रोलिसिस करथिले जो CO2 पड़ो
What?
सर कोलबेस इलेक्ट्रोलिसिस करथिले जो गोटे कार CO2 रिलीज हो जाउथला ଆମେ ୟାକୁ कार्बोक्सिलिक एसिड କରିଦବା ଆଉ ତାପରେ ସୋଡିୟମ ସଲ୍ଟ କି ପୋଟାସିୟମ ସଲ୍ଟ ବନେଇକି
Of course, this coal-based electrolytic method is more suitable for getting methane. But you get other products also. Byproducts also are there. Ester byproduct is there. If you take propanoic acid, then many other byproducts can come. So it is never recommended to use the electrolytic method for for conversion. Yes, he is saying, he is proposing, yes, it is possible. Let us oxidize it by Jones reagent and sleep for one night. Don't distill out the reaction mixture after maybe 5 minutes or 10 minutes. That means you are arresting at the aldehyde stage. So just leave it. So this will bring it to acetone. They'll give it to acetic acid. Then he is saying make it sodium salt, Na or NaOH, whatever. Make it sodium salt and take it to electrolytic method or potassium hydroxide and then electrolysis. Sorry, electrolysis to get methane because CO2 will escape and this CH3. No, this will be giving ethane. No. CH3 will join with CH3 to give ethane. So this is the best method to get ethane, not methane. Are you confusing with the decarboxylation of sodium salt by soda lime to give methane? That is the best method to get methane by heating a mixture of soda lime with sodium acetate to get methane. There will be no byproducts. But electrolytic method starts from ethane because there will be coupling. This radical mechanism I told you, I guess. So there will be methyl will be joining to produce ethane. मन पड़ला?
yes sir soda lime hit नगो
सोडा लाइम ବର୍ତ୍ତମାନ ସେ ଚେଞ୍ଜ କଲା ଏଇଠି ଡିକାର୍ବୋକ୍ସିଲେସନ କରିବା not by Kolbe's method by using soda lime, which is a combination of sodium hydroxide and calcium oxide and heat, so that the sodium carbonate will go and this H will join here, so you get methane. And then to get methane, so many steps. First bromine, H nu, heat, methyl bromide. Every time you get some product, you go via haloalkane because that is the substrate for both SN substitution as well as E elimination. So this will be bromide and then KOH ACK to give. So you see so many steps. But here, if you devise, since you are breaking into two halves, so you can make alkene, ethylene, and perform ozonolysis, reductive ozonolysis to get formaldehyde as the only product. Had there been two products from an unsymmetrical alkene, then I would have never ever recommended. So one of the methods is you convert to alkene by just Kong sulfuric acid and heat. Then you get alkene. This is dehydration. We have studied both in alcohol chapter as well as in alkene chapter. And then perform reductive ozonolysis ozone, then with zinc acetic acid or zinc water, whatever. So this is reductive ozonolysis to get 2 moles of formaldehyde. So by that you have reduced the number of carbon atoms, but you have made half. And then simply La. Or who can tell me how to convert aldehydes, ketones into alkanes? What is this specific reaction called? We have studied in the chemistry of alkanes how to get alkanes from aldehydes and ketones. What is the name of the reaction? Oh, you are damn, I cannot say weak.
ZnOHCl नहीं
ZnHCl, are you kidding me? that will make it alcohol. No. The specific reducing agent is Clemmensen reduction. What? It is zinc HCl or something else? Look to the Clemmensen reduction. Zinc
Sir,
amalgam.
amalgam.
You have to amalgamate. Yeah. Only zinc will not be helping. Zinc amalgam HCl. Yes. Or this is Clemmensen or Wolf Kissner. What is that?
NH2, NH2.
Huh?
NH2, NH2.
Sodamide, NH2, hydrazine alkali. Hydrazine alkali, it goes by oxime.
Yes, sir.
Hydrazone, I'm sorry, hydrazone, hydrazone, it goes via hydrazone, and then the reduction in alkaline hydrolysis will give you alkane. So this is Wolf Kissner, this is Clemmensen, or so you get methane. But we are interested in what?
Sir, alcohol.
No, then la, oh my God, why am I wasting your valuable time and also my valuable time? So, what is the need of making it alkane? You simply la, oh my God, you are so. La will make it methanol. This is the most economical method. How many? One, two, three. And here you have how many steps? One, two, three, four, five. So you have to look for economical conversion process. Once you revise the topics, I mean all the points, remember them and go for a good practice, then you automatically you can remember. Okay. I will make more similar problems, practice conversions as well as. Okay, anyone can remind me how to uh, distinguish between methanol and ethanol? Both are alcohols. You can't use seric ammonium nitrate because both will give a red color. So, anyone who remembers, kichi poduno, revise what koruno. And you are, to me, I'm sorry to tell you because I have the right to reprimand you for your benefit. Increasingly appearing to me as a normal, average, or maybe above average student. But really, you are brilliant students. I know for 101% severity, I can guarantee. You are, all of you are excellent. Otherwise, it's not possible to sustain with me. I have seen, this is not, I'm saying, with my experience, I'm saying that the kind of impatience that I am having now at this moment, that I will only help to those who can, resonate with my level of impatience. I can't say the word impatience. This will be not good at all.
Sir, Adderform test.
Yeah, precisely. If you, of course, haloform reaction digital mechanism we have not done. But if you treat iodine NaOH and heat, then this will give you a yellow precipitate. This part will be broken down to CHI3, and this part will be sodium formate. And the alpha carbon with respect, because this will be converted to aldehyde group. Same iodine will be oxidizing this to aldehyde, and alpha carbon will be substituted 3 times. The mechanism is very beautiful. We'll be talking about that in our. So that then alkaline hydrolysis will cleave the carbon-carbon bond to give you the iodoform. This is the yellow PPT. But here, if you do that, you will not get anything. No change. By that you can distinguish. Okay, but you take any standard competitive book that you are having. We are going to complete alcohols, ethers, and phenols. Phenols we are going to finish today, and ethers one more sitting. Ether is a small chapter, so we'll be sitting one more so that you solve MCQs and other, not only MCQs, but other subjective problems from any standard book. Don't expect me to sit with you multiple times. Of course, I know that students, they love to continue, I mean, to sit with me in these kind of revision sessions, uh, particularly the roadmap problems. I used to say, remember that some who are now in a very coveted positions, they used to tell me while they were in my regular coaching long ago, they used to disturb, I mean, interrupt me. Sir, ଆଉ ଟିକେ ଏଇଭଳିଆ ଦିଅନ୍ତୁ. I used to say, should we go for more churning of our knowledge that we have so far acquired? I coined the term churning, brainstorming, a churning. Se kahibe, sir, how to churning kariya? So sometimes we spend a whole class in churning A to Z. Z is letter, single letter is finished, then A, B, A, C, and like that. I was telling you that before. So now the remaining portions phenols to continue. The remaining portion, I have told you an interesting mechanism how you can predict the cumin phenol process is just one process of manufacture of phenol from cumin. Then hydroperoxide make it react with oxygen and air, slight warming, hydroperoxide. And while we studied hydroperoxide, we studied in general what happens to any hydroperoxide when it is subjected to acid hydrolysis. So you get which group migrates, the migratory aptitude is hydrogen number 1, then phenyl. Out of the aromatic, the plus R, like methoxy, methyl, will have greater migratory aptitude than phenyl. And still, the minus R, nitro, cyanide, all these have a lower migratory aptitude than phenyl. So after phenyl comes alkyl. Out of the alkyl, we have 3 degree greater than 2 degree. Accordingly, you have to devise what will be the product, what will be the ketone, and what will be, sometimes it will be alcohol, not phenol, because the migration, that depends on migration, which migrates from carbon to oxygen. There is a carbon to oxygen migration. That one becomes alcohol or phenol. Here, in this case of cumin, it is a very symmetrical compound, and only you have competition between methyl and phenyl. Phenyl has a greater magnitude, so that moves from carbon to oxygen, so that becomes phenol, and this one becomes acetone. It's a very simple thing. Now, I'll be taking the advantage of my PowerPoint slides and give you the home task to finish. We have seen last time, if you have, Samita, if you have got the time to watch the video, then we have seen how esterification can be done, where phenol, like alcohol, I'm saying phenol is different from alcohol completely. It's an aromatic compound. So that will undergo the acyl substitution to give you the phenyl ester, and you can use the substrate both carboxylic acid. You can also use acid chloride. That is better, much better than carboxylic acid. And it's part. Another alternative is acid anhydride to give the same compound. And we have seen the certain Bowman reaction where specifically we have acetylated. Phenol is acetylated. The same thing. I was giving a general anhydride, here is acetic anhydride to give you the phenyl acetate, no doubt. And also seen how you can benzoylate. This is phenol and this is benzoyl chloride. And the acid part is benzoate. This is phenyl benzoate. And if you take salicylic acid, and perform the acetylation, the carboxyl part will not move, will not budge an inch. It will remain because the nucleophile is this O lone pair that will attack one of the acyl groups here, and the other will go as acetate ion in a beautiful two-step mechanism, acyl substitution, and you will get here substitution. Nothing will happen here. This will not, because this is a nucleophilic acyl substitution happening to this acting as a nucleophile, and you get this OH is acetylated, but to name this, we will call it acetyl salicylic acid. Or if you become very strict, you will tell acetyloxy, 2-acetyloxy, acetyloxy, benzoic acid, 2-acetyloxy, benzoic acid. Now I'm here. What I want to see what these guys are, saying. So this was previously the phenolic OH, but since carboxylic acid was already there, it was called salicylic acid. But we are now hitting on OH, phenolic OH, which will be acetylated, esterified. And then this name, what will be the name? Let us make it look better. It's now looking better. Now the name, what I said will be the PIN, preferred IUPAC name, but it has a very popular name, acetyl salicylic acid, which is nothing but aspirin. The commercial name is aspirin acetyl salicylic acid, which is a painkiller, an analgesic, an antipyretic. Mostly it is used as an analgesic. Paracetamol, which we'll be learning in chapter amines, that will be both used as an analgesic and antipyretic. 2-acetyloxy, benzoic acid. Okay, now I would like to show you this slide to cover the remaining portion. This is Williamson synthesis of ether. You take sodium, make it a sodium salt by treating with either sodium metal or sodium hydroxide, and then treat it with a 1 degree halide, and to get 100% almost exclusive substitution product. This is alkyl phenyl ether. One example has been given, so you don't write anything, but promise me you will write everything at home. You will get anisole, methoxybenzene. And this is another commercial method, manufacture of anisole is done in sometimes in a different way by using dimethyl sulfate. Dimethyl sulfate can directly convert phenol to, I have shown you the box, which goes away. This O is bonded to CH3, and the methoxysulfonic acid is the other product, so you get anisole. And this one, I think we will be spending a lot of time. Reimer-Tiemann reaction. I would like you just write down. Because in Phenol chapter, Reimer-Tiemann, Uncle Simon Mette Piemann, going to the fair. Those who have come from the English medium, particularly the ICSE background, like Shruti Sreya, and maybe you were in Joseph Convent, Miss Misra and Miss Misra? Shruti Sreya, are you dozing? I think they have left. Shruti Shreya. Shruti Shreya. Samita, have you heard this one? Uncle Simon met a pie man going to the fair?
No, sir.
No. So that is in a ICSE book, I remember when my children were studying in ICSE. Okay, write down. It's a very important reaction. It's called orthoformylation. Phenol reacts with chloroform in presence of alkali to form salicylaldehyde. The acid that we took for acetylation to make aspirin, that's aldehyde, salicylaldehyde, I'm sorry, salicylaldehyde. And if you take exactly 3 moles to 1 mole of phenol, 3 moles of NaOH, we get a neutral product. But if you take excess, if you don't control the stoichiometry, then you get sodium salt, sodium phenoxide. And then, of course, the phenoxide of the corresponding salicylaldehyde. And then you acidify to make a neutral salicylaldehyde. Now I'm showing you, have you written this?
Yes, sir.
Now see, this is the essence of the reaction. Phenol treated with chloroform and exactly 3 moles of KOH or NaOH give you salicylaldehyde. Now see how it happens. First, it forms, the ortho position is substituted by CHCl2. Out of 3 chlorine, 1 chlorine goes as chloride ion. I will show you the mechanism. Then the other NaOH will make it aldehyde. This will be undergoing hydrolysis. There will be 2. 2 moles of NaOH are required to make 2 chloride ions to go, and 2 OH will join, but geminal diols are unstable to give you aldehyde. And then acidification. Of course, here we have already used more. We have not shown you. Excess of NaOH have been used, so acidification is needed at the last stage. And this phenoxide has to be brought down to a neutral form, OH, by acidification. Now I am showing you first the mechanism. Chloroform, agar OH minus gola, that also, the OH minus here abstracts a proton and produces a carbanion, trichloromethyl carbanion. And then chloride ion is eliminated to produce a neutral intermediate species called dichlorocarbene. You already know about carbenes, nitrines, and all that. A singlet carbene, triplet carbene, and what is the hybridization of carbon you have not revised. That's a separate story. So this carbene now is the electrophile. You remember that although it has a lone pair, carbenes are electrophiles because it is sextate, electron deficient. They will accept electron acting as an electrophile. So what happens? This OH minus will first remove this proton to make it phenoxide. If you look to this portion, which is an enolate ion, it will look to this portion only. Then the real nucleophilic center will be carbon. Carbanions are more nucleophilic, more basic, more nucleophilic than alkoxide. Therefore, when attacking comes, immediately it attacks via the carbanion. So it will come, ortho position will attack, and it will attack the carbene to produce this one. Again a carbanion. I will write down myself. Just listen to me. C. Then proton transfer from the orthocarbon to the dichlorocarbene portion, that aromatizes. The aromaticity is restored with phenoxide ion is produced. Then what happens with another mole of KOH? What happens? This one of the OH minus substitutes a chloride to produce OH. And there is again a proton transfer and bond transfer, another chloride ion goes. So the third mole of KOH will make it acetaldehyde. But actually, it's not like that. We don't always look to this stoichiometry 1:3. We take excess of KOH or NaOH, KOH. Then last step is acidification. So let us write down the mechanism. And later on, I will tell you why ortho, why not para. What factor is responsible to make ortho as the absolute major product, not para. What is the reason behind ortho selectivity? I took a 1 hour seminar on this point while I was training the teachers in to the DAV postgraduate teachers who are teaching you guys in that training program happened in DAV CS-Pur, Bhubaneswar, Chandrasekharpur, where all the DAV teachers from different places they attended. So they wanted to discuss why the orthoselectivity, what prevents para attack, because that can go to para. It can just, you make another resonance, then it, the double bond comes to the vertical position and carbanion can be formed at the para position to attack. Why not then para? What is the magic happening there? We'll not talk about that later, but we will definitely go for the mechanism, because I will not leave that. Reimer-Tiemann. Reimer, R-E-I-M-E-R, then T-I-E-M-A-N-N. Reimer-Tiemann reaction. What happens here? The phenol reacts with, if you take chloroform, of course, is read it. If it's 3 moles of NaOH or KOH, usually KOH is taken to give you, this OH remains and this, the ortho position is formulated. Of course, in the process, a lot of chloride ion will go 3 KCl. You can write down 3 KCl. Don't worry. But, or if you take excess, remember this is really and KOH excess, then you get this one. Aldehyde is not an acidic compound. This hydrogen is not acidic, but this OH is acidic. It will remain as sodium salt of phenol, salicylaldehyde. Salicylaldehyde is acidic not due to aldehyde, but due to OH. But salicylic acid is acidic both for carboxylic acid and phenol. Both are acidic. Both carry acidic hydrogen. So this, you have to go for acidic hydrolysis, so that add little bit of acetone, sulfuric acid, dilute sulfuric acid and distill out. This will be neutralized here, OH. This is salicylaldehyde, the name. And this is 2-hydroxybenzaldehyde. The IUPAC preferred IUPAC name is 2-hydroxybenzaldehyde or salicylaldehyde. Okay. Now coming to the mechanism where we can show really 3 moles. If more, then also I will tell you what happens. How carbene intermediate is first chloroform. The OH minus ion from KOH now first produces a carbanion. This then undergoes alpha elimination in 2 steps. This is what we call alpha elimination. This 1 chloride ion goes, nothing happens. Only 1 chloride ion goes. So the electrical neutrality is maintained, but lone pair remains intact. This is dichlorocarbene. Is ready now to attack. Now coming to the aromatic moiety, phenol. I'm deliberately keeping double bond here. With 1 mole, this is the first mole of OH minus. So that will remove, so that you get the corresponding phenoxide ion. So water is removed. Then see what happens. It reacts with the dichlorocarbon, which is already, we have shown it how it is formed. But when attack happens, it attacks at the orthocarbon. Oxide ion is not a good nucleophile compared to carbanion. Therefore, enolate, as we have studied enolate ions, whenever they go for a nucleophilic attack, they transform, they remain as enolate. Enolate is a stable ion. Maximum percentage remains, maybe 99% remains in enolate. O carries minus charge. But whenever there is a situation to attack, the negative charge to attack, the negative charge, the lone pair doesn't attack from oxygen site, rather from the carbon site, because there is always a resonance. It can come during attack. So this comes here, and this pi bond now attacks at the ortho position. This is the ortho attack. Why ortho? Why not it goes here and para attack? We'll learn that later. But what happens is this becomes a double bond, and this, sorry, and since it comes, lone pair is there and minus charge is also there, because we have to show the conservation of charge. There was minus charge here, no charge here. Since this is the donor, this carbon is the donor, this is the acceptor will carry negative charge, formal charge will be going to carbon. Now what will happen? There is a proton transfer. Immediately there will be a proton transfer, the aromaticity. Three things will happen. This will abstract a proton, and this, I'm sorry, I'm so sorry. Not from the ortho position. I mean to that, same position. It will abstract. And this sigma bond will be turning into a pi bond here, and this will be polarized to give you phenoxide ion. But already aldehyde group, dichlorocarbon methyl group, dichloromethyl group is added now, is attached now. This will be O minus, and this aromatic structure has been replaced. So this will be having CH. There is no need of, so we have so far used how 2 moles. 1 mole has been used to convert chloroform into carbon. The second mole has been used to convert phenol into phenoxide. And see where the third mole will be used now. OH minus from another third mole of OH will remove another chloride. So another chloride will go. So OH will come, and of course H is already there. So OH will come. Now simply proton transfer. And this will come here, and this will go automatically. So automatically proton transfer with the formation of a double bond O and removal of Cl minus, that will be all taking place in one go, and we get our compound OH and CHO. So the third mole exactly. But usually what happens, if there is excess KOH, so that will take away and it will put it as the phenoxide ion of the salicylaldehyde. Then you have to go for acidic hydrolysis to get back the neutral salicylaldehyde. So these steps are optional. If you take excess, write down excess. More than 3 moles. Therefore, usually excess is taken. Minimum 1:3 needed. So who bothers about calculating exactly 3 moles of 1 mole? Add excess of KOH. What will happen? It will remain in the salt form. Om Swaha. Ashidaya Swaha. And then ultimately you get back the normal neutral compound. So this is the beauty. Okay. Lecture learning?
Yes, sir.
Miss Tripathi?
Yes, sir.
Miss Misra and Miss Misra? Shruti Shreya, you
Yes.
are you listening to me?
Yes, sir.
Very good. Excellent. Uh, Now, another similar process is there. If you take phenol instead of chloroform, if you take carbon tetrachloride, CCl4 and excess of NaOH or KOH, then instead of getting salicylaldehyde, you get the salt. Whenever there is carboxylic acid, which is a stronger acid than phenol, so the salt will be CONA. And then acidification will give you salicylic acid. So the mechanism does not involve a carbene here. It simply attacks one chloride ion goes, no generation of any carbene. Mechanism is similar, ortho carboxylation ortho, and there will be CCl3. Very simple mechanism. NaOH will make it O minus. Then this enolate ion will come here and this ortho attack will happen to this. One chloride will go. Then CCl3. And again OH, excess of OH minus, OH minus, ON minus will make it OH, OH, OH. Geminal triol is also unstable. So one water molecule goes to give you carboxylic acid. But since excess of NaOH is there, it will remain in the form of salt until you swaha, acidify as namaha. You got it? So salicylic acid, other variation of, this is another variation of Reimer Timemann reaction is instead of using chloroform, you take carbon tetrachloride to give salicylic acid. Now this you will be writing at home. Here this is hydrogenation, just like we found that the double bonds are being saturated. So the aromatic properties destroyed, become cyclohexanol with hydrogen, nickel or palladium or platinum and heat. Hydrogenation occurs. And these are simple because we already know OH group is a very strong activator. It activates the ring with resonance. The orthopara positions are electron rich and they act as a potential substrates for electrophilic attack. Orthopara positions are very, very electron rich due to strong plus R effect of OH group, and the electrophile attacks at those positions, both ortho and para. You get a mixture of ortho and para. Now you will write at home very meticulously. If you used MA, then situation will be out of control. You get all the favorable position, 2 ortho and 1 para, all substituted at one go. You get picric acid, 2,4,6 trinitrophenol. This is famously called picric acid. But if you want mononitro, then you have to use dilute nitric acid, not sulfuric acid, not also conc. Then you get a mixture of orthonitro and paranitro, since it is the OP director and activator. It reacts faster than benzene for any electrophilic substitution. So since nitro is not a bulky group, not much bulky group, so it will be nearly equal yield, maybe 60-40, 55-45. So that will happen. Still, ortho has a greater chance. If there is a bulky group, for example, now picric acid is really manufactured in different manner, not in this manner. It's inconvenient to prepare picric acid commercially from phenol by nitration using Ma. Yes, nitration will happen, but the leaving group has to be different. So first, fuming sulfuric acid will make it sulfonic acid. Sulfonation will happen at the para position almost exclusively because SO3 or SO3H plus, the electrophiles are bulky, so they will prefer to go for the para position rather than experience steric hindrance. So you get and in excess of fuming sulfuric acid will make it at the most disulfonic acid. This is disulfonic acid, ortho and para. Then once you add with conc nitric acid, instead of adding a mixture of conc nitric acid and conc sulfuric acid, if you first sulfonate it 2 times, 3 times it's not possible. So it will be so deactivating and the steric crowding will be so high, it's not possible. Then add conc nitric acid and heat. You will find this SO3 2 minus will be the leaving group here, and you will be getting at the same time there will be 3. One H plus is the leaving group, the other one is SO3 SO3H plus, I'm sorry, this is electrophilic substitution. So here NO2 plus will substitute SO3H plus, SO3H plus and H plus at one go to give you picric acid. I was just thinking about a nucleophilic substitution. SO3 2 minus was the leaving group at that time. Sulfonic acids are very cool. They act as a very good leaving group, both for electrophilic as well as nucleophilic substitution. Now you will write this at home. Halogenation with chlorine and bromine in presence of non-polar solvent like carbon disulfide. Particularly bromination is used in carbon disulfide to give bromophenol, ortho and para. Para is the major because bromo is a bulky group. Here the halogen carrier is not required like alkenes, arenes, which needs for halogenation you need chlorine FeCl3, bromine FeBr3 or simply Fe. So such a thing is not required because this is so very activating. The orthopara positions are so electron rich that there is no necessity of any help or any aid to produce more electrophiles. So Br will give you Br plus automatically by the heterolytic cleavage, and the Br plus is the electrophile here. And now similarly, if you add bromine water instead of using a non-polar solvent, if you take water, then the polarity is so high that at one go, all the 3 positions will be substituted. 2,4,6 tribromophenol. That is a white precipitate will be formed if you take bromine water. Sulfonation, I have told you, phenol is monosulfonated. Not this one needs a higher fuming sulfuric acid. So simply here also, if you take go for a monosulfonation at a lower temperature, particularly lower than room temperature, then sulfonic acid will be ortho substituted. This will be the major product because there will be hydrogen bonding between H plus delta and minus delta here, so that this will stabilize the ortho isomer. Low temperature, there will be hydrogen bonding, intramolecular hydrogen bonding. But if you have a high temperature, between 25 to 100, there will be a mixture of both ortho and para because the hydrogen bonding starts breaking intra. And above 100 degree, the exclusive product will be para hydroxy sulfonic acid. Now, Friedel-Crafts reactions are absolutely unfavorable here. Nobody does because the aluminum chloride competes with phenol. Phenol reacts with aluminum chloride because it is a donor lone pair. So the electrophile nature, the Lewis acid nature of aluminum chloride is destroyed by phenol, and it cannot generate the electrophile CH3 plus to attack. Therefore, very slow reaction with Friedel-Crafts alkylation because the ring is deactivated. And moreover, once aluminum chloride joins with phenol to form a salt, O carries a plus charge, then deactivation occurs like nitro, like carboxylic acid. So deactivation of the ring slows down the reaction, although you can use excess of excess of aluminum chloride to produce the carbocation CH3 plus, although it is 1 degree, which is not formed, I have told you, but it goes an ion intimate cation and ion pair, AlCl4 minus and CH3 plus, they go for intimate, and once it attacks, AlCl4 minus goes away to CH3 joins. But that not happens easily. It's very, very slow and nobody favors. Kolbe's method is another way to get carboxylic acid. Here, you first make sodium salt by using sodium hydroxide and then bubble carbon dioxide with a high pressure, 4 to 7 atmosphere, with high temperature, 400 Kelvin. Then you get that O minus will go for an ortho attack, just like you have seen to carbon dioxide. One of the C double bond O is polarized to O minus. That becomes, and it becomes sodium salicylate, and acidification will give you salicylic acid. So Kolbe's, not Kolbe's electrolytic method, simply Kolbe's reaction. This is ArSE. This I've shown you the mechanism here. Now, this is the electrophile. Carbon dioxide, all acidic oxides are Lewis acids and hence electrophile. And this acts as a nucleophile. And this is electrophilic substitution of just like we were doing nitration sulfonation. Here the electrophile is neutral CO2. It attacks here and one of the bonds becomes polarized O minus. Then proton transfer brings about aromatization. Then acidification will make it salicylic acid. This simple, very simple mechanism. And also you write when you open the bottle of phenol, it looks dirty. I mean, it looks pink because of the formation of small quantity of parabenzoquinone. This is the substance which is not aromatic. It is non-aromatic, parabenzoquinone. Either you leave it open or, I'm sorry, I'm leaving it here, or use an oxidizing agent, you get parabenzoquinone. That's all for today. Have a very good day. Bye-bye. See you on Thursday.
Sir.
Thank you, sir.
Pranam. Have a good day.